Hi, my name is Sarah Chang. I'm the head of DevX at Cerebras, and we are joined here today by Sara Hooker, who is the author of the famous essay Hardware Lottery, among many other achievements. Sara, would you like to introduce yourself?
Yeah, it's lovely to be here. So I lead Adaption, which works on continuous learning, and also I feel pretty passionate maybe about certain things we're going to talk about, like how do you make algorithms work better with systems, and how do you create super efficient learning. The hardware lottery is really this idea that hardware has determined pretty much everything in computer science progress. So as researchers, we're super attached to our ideas, and we believe that they have a lot of elegance. But actually what the hardware lottery tells us is that time and time again, it's been really whether an idea is compatible with hardware that determines whether it succeeds or fails. It has like profound implications as well for like where we go next, which is kind of interesting.
So I'd like to now pivot on what you're working on more recently, which is adaption. The way that I understand the thesis of adaption is that it's about continuous learning and the ability of the model to learn from new experiences instead of relying on models to come pre-trained from static data sets. So continuous learning has been one of the great unsolved problems for over 30 years now. Why do you think it's become so relevant today?
Continuous learning matters a great deal in long task horizon settings. Like if you think about it, what's the goal of continuous learning? Is that you can add capabilities while retaining performance. It's the idea that, you know, when we graduate from high school where we don't have static knowledge, we like can learn new skills. We can go scuba diving, for example, and we won't just forget how to write that we learned in 12th grade. And like, what's interesting, I love your chuckle at that one, but it's true. I think it's like balancing all these capabilities, but where that becomes extremely important is if you have long time horizon tasks. And now we want models to interact with the world. And if you think about that, it means that you have to make a sequential set of decisions that compound. And it also means your search space is huge. So anything that you can do to improve the efficiency of that search space by changing model behavior every step of the way is really important. Like most RL rollouts right now kind of pay in cost to learn a space. They're super inefficient. You basically make it almost like a semi-supervised problem because you do so many rollouts, you just exhaust the search space. But the truth is, in the real world, you just can't do that. Maybe you can do it for a game, but you can't do it as you navigate complex decisions in different environments. And so the idea of how do you add knowledge and how do you update very quickly becomes central. And that's why continuous learning is very much back in the conversation, because we're back in the wild, wild west of we actually have to take like sequential decisions.
Of all the different ideas that you've seen about how researchers across the world are approaching continuous learning, what are some of the approaches that you're seeing, and then how does adaption kind of play into that?
Perhaps like I'll share instead like what I find most boring to most interesting. I'll be a bit cheeky. Like I think the most boring stuff is probably like what is already like some production solutions to this, right? Like oftentimes at big companies, you end up just retraining the whole model periodically. And like that's kind of boring because firstly, most problems in the real world don't cleanly fit into not only you having new data that you care about, but existing data so you don't erode capabilities. But secondly, it's probably the most costly way you can deal with this. It's basically like redoing high school over and over again.
And is this what we're seeing the biggest model labs do?
You know, I think that we are seeing it in production settings. To some degree, we are seeing like a lot of, and this is not specific to now, this is typically how people have dealt with this problem. We are also seeing a lot of companies treat it like a LoRa problem. So maybe you don't retrain the whole model, but you basically have thousands of LoRas, which is also nuts because then you're hosting this infrastructure of like so many different LoRa types, and you have to remember what you train for what, and also it ends up like, oh, I just always have to add another one. Which again, for me, like if I think about where innovation is going on the scale, I would place like here, like kind of, okay, yes, maybe this is a patch for production now, but it's not where you place a bet. And it's certainly not why you start something that is very important. Because really what I care about more is I care about like how do we train a model to be flexible from the get-go. So like understanding like firstly how do we post-train and align in a way that a model is maximally flexible. And I think another interesting bet is like, if you know your hosting, you know you can infer a lot of attributes about the types of problems. And so then how should you change model behavior? And you should, because there's no reason to ship the same model to everything if you can infer real time like what the type of task is. You should be changing. That's way more interesting. I also think at the most interesting scale, like going over here, is like researchers who are really thinking about the balance of parametric and non-parametric. Like really, as we think about, you know, some of the sequential kind of processes, and also the fact we want to do real-time learning, we have to think about balancing like gradient-free methods with more traditional like alignment optimization methods. And the truth is, like, the most powerful is going to hit hard on both and going to do innovation in both spaces. And like that's pretty fun. I think that's one of the most central questions. And like everyone has a different flavor. Like some people are like, oh, we're just a memory only kind of algorithmic shop, which I think again is kind of boring. And probably the most innovation has come from people who do both very well, but also care about the hardware stack and co-optimize for that, because that's going to matter more and more.
So one thing that you've talked about before is how chatbots are not the natural interface for, or the best way for us to interact with AI agents. What would you say is like a more natural interface?
I just think I think it's two things. Like one thing is that when you ship the same model to everyone, you basically make them do acrobatics around the model. So it's both that it's a chatbot, but we're insisting that everyone be expert prompt engineers. I think that also a lot of the people around the world don't like to type, like they use voice. The main thing I think is that it should take you way less time to get what you want from a model. And that involves both like at the model layer adapting, but I ultimately think the interface should change based on what you're doing. Right now, like you basically are always consigned to chat, but depending on what you're doing, you might need different tools at different times. That's why our third pillar is really these interactive interfaces, because we think, you know, the original vision of the internet was that things would be summoned to you as you needed them. And instead we just have hundreds and hundreds of tabs these days. And I actually think one of the core things that is meaningful is how can we go back to that original vision? And a model should be able to anticipate like what you need when you need it, and the interface should change in a way that doesn't feel disruptive, but feels like it's still cohesive with what you want to do in your day. And that's important as well, because that gives you the chance to give way better feedback about what's not working. One of the reasons people don't give feedback right now is that they don't feel like there's any instant change in model behavior. But if the interface better represented like how you go about your day, there's also way more chances for you to signal like this isn't what I like or how I like to do things.
Now, and to the point of interfaces, I mean, even when you look at the two major model labs, OpenAI and Anthropic, and how we have Codex, we have Claude Code, we have them taking their own approaches for how they especially target the non-technical audience. We have like Claude Coworker. As we build more levels above, you know, the agents, so that, you know, if you want a multi-agent orchestration, Codex does all that for you. You don't even need to say anything. It kind of builds it out itself. So as we build more and more layers and we become even further from hardware, do you think that this will exacerbate the hardware lottery problem?
Oh, in what way? This is fun. Okay, tell me more.
In the sense that, you know, we have the hardware, we have the models and the architecture. Normally, the person on the other end of that, you know, I'm using this coding model and I'm still very much in the weeds of figuring out, okay, like this is what my setup is going to look like. This is how what my compute costs are going to look like. This is how I'm going to balance it. But now Codex or Claude Code is doing all that for you. And so you're even more removed. I could be a vibe coder and I have no context whatsoever, and I'm using this product and I have absolutely no idea that I don't even know what a GPU is.
Yeah. I think it's a super good point. It's very true, because typically it means people can't tell when something is wrong, which is one of the main drivers for how you make things better, especially compatibility-wise. A good example of this was the recent drama around, I guess, API throttling, and people couldn't even tell that some of it was like a bug or a decision on a certain frontier AI provider side to change reasoning to a different level. And because you don't have profiling of that, you can't actually isolate the issue, but it's changing your model behavior. And so I do think that's true. I think that as long as there's enough cost, though, to hosting these models, and there's enough of a, I guess, a trade-off for like how do you, if you don't co-optimize at all, it's a lot more costly. Some people will care and be deeply invested, but you're right. Like the amount of people who can weigh in and be like, this is not optimal, we should do something different. It becomes slightly diffuse if like no one can see into the system. So in that sense, yes. The question you have to ask is, are those people equipped to suggest what's next? Right now, the number of people who can have a valuable opinion about how the algorithm needs to change, how the hardware needs to change, is unfortunately still very small. That's actually, I think I've spoken about this a few times, but it's actually one of the issues, right? There's a few hundred people who have this joint expertise, and they're all at the same group of frontier labs, and yeah, we all know each other. And like, I think that that's kind of the issue. So even if we improved visibility, I don't know if it would solve for the next hardware lottery, but certainly it would catch silly mistakes, and it would catch like serious issues that were impacting like a lot of different users.
No, I think that's a great point. I mean, ultimately, the only people who are going to be aware of hardware is, people working at the hardware level or researchers. And luckily, those are the ones who are informing the decisions. I do think one thing that's interesting that we talked about earlier today was how, especially if you're on the user level and you're buying these Cloud Code subscriptions and these Cursor subscriptions, all of these model subscriptions are so heavily subsidized, and like you're spending $20, but who knows how much it's actually costing to train the model, and the electricity and the energy and everything that's just bringing us even further from reality in this current state.
Oh, 100%. I think that's a very good point. And I do think it's a temporary, I guess, decoupling. What's interesting is we see some providers going towards usage-based billing, and you completely see the attitudes of developers change, because they're like, oh crap, like my agents cost so much money, I've got to kill all of them, can't let them run. And it's really interesting because then people start really caring about efficiency when the subsidies aren't passed on. So I think that's going to be an interesting phenomena as more and more companies switch from this like eat the buffet to like, hey, we've got to be real, like you have to pay for your usage, how it impacts developer behavior. It's kind of the same as like, so software was very lazy for a few decades because Moore's law meant compute basically meant you could be super lazy with software. Like we were just getting more power and more capacity every single year. Now software really matters again, and we care a lot about efficiency, and everything matters. The same will go for this. I think developers will care a lot more about what's happening under the hood once they're fully internalizing the cost of what's happening.
Hardware Lottery was written in 2020. What has happened in the 6 years since that was written?
So what have we done over the last 10 years? Like what's happened? I think a lot of what's happened in the last 10 years is there's a reason people move towards optimizing for deep neural networks. We had this really great return for compute that was applied to scaling. And so a lot of the last 10 years, even as a researcher, like building frontier models, if you think about it, you are trying to throw the most compute at like pre-training size, trying to blow up your model size, trying to squeeze the most out of transformer architectures, prior to that just deep neural networks. And so a lot of that is what I would call like a predictable workload. It's not an easy workload. Actually, like one of the most dominant shifts that happened with that whole era is that we went towards like really specialized compute, right? Like instead of doing general purpose, which was a lot of early computer science history, we're designing TPUs, Cerebras. We're specializing in things like, I guess what NVIDIA colloquially said is like the transformer architecture, the transformer version. And it's very interesting because all this is a bet on like, let's make this one thing as big as possible. But we're in an interesting moment where like pre-training size is not the only thing that matters anymore. And that's pretty interesting because we see now that you can't just double the size of the model and get predictable gains. This is pretty, I think in some ways normal, right? Like you discover an idea and then you exploit it to the max. And we're kind of at the ceiling of transformer. But it means that the meat is no longer in like sizing up that first dynamic of like the size of a model and how you co-locate and train it. A lot of it now is, and a lot of the innovation is, how does a model interact with the world? And the rate of return for compute is not as high in pre-training as it is in post-training and test time compute and all these sequential processes. And the thing that drives most innovation is like, what is the rate of return for the compute? Where can I get the most bang for my buck? Those are the types of ideas that have massive leverage when you apply compute to it. And that is dramatically changing. And like, what does that look like for the hardware landscape? These type of innovations, and like, I think in adaptation, like one of the things that we care about the most is how a model evolves with the world. That involves interaction. It requires a lot more thought process about how does the model handle things like inference or like multi-stage, and you named a bunch of it. And for those, it's not just the GPU, it's also how you think about things like memory. Like if you think about your GPU and like you think about a frontier AI lab, and maybe, you know, if from my perspective, frontier AI labs, they're kind of like massive factories of some kind. And like you have scale in the jobs that you serve, that you train, and you also probably serve in your models. So you care about efficiency on both sides. And let's say your factory is like baking cookies, which is a funny metaphor because I don't bake, but I think like a lot of the obsession with GPUs and scaling is like, what's the biggest oven? Because we know that all we're doing is baking cookies. And now a lot of it with agentic workflows and different things is, well, actually, we need to bake personalized cookies for everyone. So it's not just getting the dough to the oven. It's like there's different stages and different amounts of steps to each cookie. And that's where it matters much more things like memory, and it matters much more things like how do you handle this branching and complicated routing. And for that, I think co-design of like both algorithm and how you serve is super important. Like one of the most important criteria for us is like we want real-time adaptation. To do that, you have to be almost obsessed with this co-design of like how you serve and how model behavior updates. And I think that's the crux of innovation, but it's a pretty dramatic change. Like that is pretty profound if you look at the last 10 years versus where we find ourselves now.
And you came from a researcher background, especially when you wrote this. And so did you have certain exposures to hardware, or were there certain things that motivated you to write this specifically?
At the time, I was at Google DeepMind. So actually, at the time, it was Google Brain before it became the hybrid that we know now. And I was working on sparsity. So sparsity is like one of the most notorious examples of an elegant idea that just doesn't work in practice, mainly because it's just not compatible with current hardware. And so that got me thinking, well, how do we get there? If we know this idea is so much more elegant, you can achieve, and sparsity, by the way, is the idea that you can squeeze and basically delete large parts of a deep neural network, and you can end up with something way smaller after training. And unstructured sparsity is the most powerful form of this, but it basically slows everything down on hardware. And so it was like, how do we get here? And why will this be a problem that's unlikely to be solved even in the next 10 years? And I just found that super striking. And that's when I really became interested in the fact that actually we've had massive hardware lotteries since the very beginning, since Babbage's computer, thinking about like deep neural networks, probably the most famous one. And that is pretty crazy because deep neural networks, if you think about it, all the algorithmic pieces were in place since the early 1970s. Like backpropagation was invented in the 1970s, then it was invented again in the 1980s, and it was paired with Jan LeCun, like that was his major contribution. In 1989, he paired it with convolutional neural networks, but then we had this massive gap. It was only in 2012 that deep neural networks were a success. And so when you take a wider look, these hardware lotteries have defined some of the major swings in like what we think is important and like what people work on, and they've delayed major breakthroughs a lot of the time.
And earlier when you were talking about sparsity and them being very poor for the current hardware, are you referring to GPUs?
Yeah, basically GPUs are very unfriendly towards anything but very particular patterns of sparsity, structured sparsity. So because GPUs really like matrix, very defined bulk workloads, and unstructured sparsity is the opposite of that, right? Like you have missing parts of the network where you've like carved out parts of the deep neural network that you don't think matters. And so it takes far too long to figure out where those sparse pieces are. So it slows everything down. And so it just doesn't work.
So can you be more specific? Is it like a memory? Is it you're not utilizing the full GPU? Is it a scheduling problem?
If you think about it, like GPUs are very good at one operation only, matrix multiplies, and those are dense operations. Like where a GPU is happiest is if you keep on feeding it the same structured data again and again. If you have sparsity, sparsity is an old idea. Like there's a paper, I think, again in the 1980s that's called Optimal Brain Damage. I actually think Jan might be on that one too, which is kind of fun. But there's a series of papers which are basically let's decimate a network. We can make it much smaller afterwards by just choosing parts of the network that are not important. What that means though is that you're kind of poking holes on your big matrix. Like the weights are now sparse. And what that happens is when you get to the GPU, you can't just do a matrix multiply. You have to remember which parts of the network are meant to exist and not. The hack that people do is they just put zeros there, which is weird because you're not actually improving efficiency at all. But that's an example of like how our hardware is very much created to optimize for one thing, which is a single operation, and that happens to dominate what our current networks are. So like 90+% of your network architecture is just matrix multiplies, and that single operation over and over again. But it's not necessarily what the architecture of the future will look like.
So why is matrix multiplication not the correct way to think about the shape of data?
So I think a lot of matrix multiplication just assumes that you have really homogeneous jobs. So we basically stack all of our data, whether it's images or words or audio, we basically pack it. So you have these batches and their stuff into matrices, and you don't have the ability to have missing data. But one thing that's remarkable about our intelligence is our ability to process a lot of very sparse unstructured data. Like we discard most information, we only process some, and we don't have to solve for it by like filling in zeros where we don't have data. And that gives us a lot of efficiency unlock. So one of the biggest questions is, when can we switch? Basically all of computer science has been built around the idea of a matrix. Even before matrix multiplies, the idea of information being in a matrix has been very core to like a lot of our techniques. And the question is, one of the most important ones, how do we deal with sparsity? And how do we do it efficiently?
Are there popular models that we're seeing today with really sparse architectures, people are putting in zeros, that are running suboptimally?
I would actually take a wider view. So sparsity is one thing. That's what got me involved in the hardware lottery. But what's interesting is that a key component of the hardware lottery was that, hey, this happened. Deep neural networks were slowed down for basically 2 decades while the hardware caught up, and only unlocked in 2012 when like GPUs were retrofitted. But I think what's interesting is that we've only amplified that hardware lottery since, right? Like all the hardware we've developed since is basically for matrix multiply workloads for deep neural networks. And actually, I think what's interesting is that, sparsity is one example. It's mainly for like, how do you tear out parts of the network that you don't care about? But there's a ton of workloads now that are really stress testing the hardware lottery. Because for example, like as soon as you move towards an agentic workflow, or as soon as you do RL in an online setting, you're in a totally different paradigm, right? Like you don't have predictable memory patterns. You're not maximizing just for throughput because you don't have a predictable in and out. And like that's kind of interesting to think about, because that's actually a major shift that's going on right now. We're moving from just like building the biggest model to like building models that interact with the world. And that type of sequential, like what do I do after I do step one? That isn't what really GPUs are good at, because it's a routing and it's a cascading decision sequence. And GPUs are not good at that. They're good at being like a baking factory. They're good at applying the same oven to the same recipe over and over again, which is really interesting to think about. And so actually I would argue like our hardware lottery situation is even more dire today. It's just that we don't quite realize we're in it right now.
And this is something that you mentioned in the original paper as well, this kind of the balance between building something that's general versus specializing. The GPU is a very general purpose solution, but then we're needing to bake all of these individual cookies. So for a researcher today, how should they think about this balance? How should they invest?
I would say for a researcher today, don't do pre-training, because there's less rate of return there for your compute. Of course, there's very few researchers in the world who can do pre-training to begin with, but I'm speaking from a frontier lab perspective as well. Like where I think compute is going to go is most innovation pre-training that frontier labs are doing is in the data space. Arguably, like they're doing super interesting synthetic recipes, but they're not. I would say very few labs are going to like quadruple the size of their model right now. Mm-hmm. Instead, like in some ways, this spells the era of innovation, right? Because it matters much more what is your post-training recipe, what is your test scaling, how you interact with the world. This is fun because in some ways it opens up again. It's the person who has the best recipe, not the person who can throw the most compute at pre-training. What that means is, it means a few things. One is that you have to care, if you care about alignment and exploration, you have to care about basically the time it takes between you inferring something about the world and the feedback to your model. And that is interesting because that's almost like two different modes of hardware. Like GPUs thrived, and a lot of these hardware types thrive because it's like data in, data out. You just have to maximize how much dough is in the oven. And like that was it, right? You just want to maximize your throughput. A lot of other details like oven gets too hot, the whole thing destabilizes, but just to simplify things. Now it's actually super complex because it's not just data in, data out. It's like once you've cooked your batch, you want to ask like, okay, I want to do this separate recipe based on like whether there's verification. I want to do this based on whether the quality is good. And I want to not explode my context because like a lot of these agentic workflows, basically you're exploding your non-parametric as well as like your parametric learning. So that's pretty wild. And if I were to say one thing, it's like researchers who figure out the optimal rate of return for that type of operation who are going to do super innovative stuff in that era. But it's fun because it means that I'm a researcher. I care about the success of my ideas. I have to be obsessed. And like my, Sudeep is my co-founder at Adaption. He makes GPUs go really fast or any type of hardware. I think his main specialty is systems. I have to be obsessed with us figuring out together how that sequence of like these super complicated now branching recipes does extremely well on the current hardware. And that's a wild challenge. And that's super interesting again.
And what are some of the directions that you guys are exploring in terms of how to make things faster on a GPU?
We care a lot about real-time adaptation. And there's a reason why. Like I think, our goal is to build intelligence that continuously evolves. So much of that, like if you think about it, is to allow a model to interact with an environment and to explore an environment very quickly. And the unit time of like how quickly a model updates behavior determines everything. It determines if someone's willing to give feedback, because someone will only give feedback if they feel like it doesn't go into a pile somewhere in some researcher's drive. Like it's not thumbs up, thumbs down that never changes anything. But it also changes how efficient a model can be at exploring. And so for that, like we care a lot about, hey, how does this scale? Like what are the dynamics of this approach versus another? We just released, like we have 3 pillars: adaptive data, adaptive intelligence, and adaptive environments, because our view is, whoa, the whole stack should be adaptable to what the problem is. Like we shouldn't be spending a bunch of compute on very easy problems, and we should spend a lot of compute on very hard problems. But that's very interesting because that's exactly these type of adaptive workloads is exactly where you need to be super careful from a systems perspective, because you're basically changing real time how much compute you're processing, and that takes a lot of innovation, which is really interesting because it's really not what GPUs were cut out for, right? They were really cut out for, hey, you have a very predictable workload, your memory access is going to work in a very specific way, and we're just going to run it through.
One of the things that you talked about earlier is some of the challenges that you're facing to specifically adapt to the GPUs that you guys are working with. Can you walk me through some of that?
A lot of it is because we care so much about efficiency and like fast processing, but I actually think a lot of probably what's different about us is that we're co-designing very closely. Like, so our serving and platform teams and our modeling teams are basically co-optimizing everything about how we think about all 3 pillars. What I would say like is the wider challenge, if I think about like, hey, if we're looking at the industry as a whole and what people are grappling with, is really a shift towards having to do much more sequential processes and also having to handle memory in much more interesting ways. Because traditionally, the main goal of optimization of hardware is to make sure that you get data to your processor as quickly as possible. But now you're doing all these side quests. So you're saying, okay, we did one run through this model, but now we're going to check and do some verification. And that is not at all suited. And this is like the interesting part. It's not all suited to the current setup, which means that it's going to be a fun bonanza for like systems people. But it also means like it's actually a really interesting era of like innovation drivers in incentives, because not only do we currently have a compute crunch where people really value how do we squeeze the most out of compute, but also we have a change in the type of compute that produces the best results. And this is crucial because most hardware lotteries occur because the idea is not commercially valuable enough to build hardware around it. But right now, these ideas are commercially viable enough. And so we're seeing all this innovation, for example, in memory, and all these different types of memory come onto the market promoting innovation, because you have this really weird historical confluence that almost never happens. The idea that's not working well with our current systems is also an idea that makes money, which as a researcher is very fun, because you rarely have the idea that you care about also be able to realize so many resources for you to make progress on.
No, I completely agree. We're doing all these workarounds and band-aids because of GPU memory limitations. Can you give some specific examples of what maybe a researcher, a pre-training, post-training researcher might be doing as a workaround, or even, sacrifices we've made in some of the most prominent model architectures today?
There's two separate parts to this question. Like, how has memory driven the architecture as a whole, what we know as deep neural networks? The other is, how is this chaos now of needing more memory than ever before very quickly caused even more changes? Like, the first is pretty intuitive. I think all the things that we see around quantization, KV cache treatment, these are all like hacks to extract more out of our memory. But that's within the old regime of hey, we have this predictable workload, let's just squeeze, let's just make sure our memory is good enough for high throughput. Now we add the chaos, and you can see that no one knows the answer. And the reason why is that you see a million agentic harnesses appear. And you see all of those trying to solve for the core issues in different ways. And what are the core issues? So when you're doing these sequential interactions with the world, you typically have very non-predictable memory access problems, right? Because you're going to be branching, some of your branches will terminate, other samples you'll want to sample much more because you're doing adaptive compute. You also have what I would call super interesting changes in how much you're off-putting to CPUs. Basically, you are using CPUs much more throughout the process to check outputs, and you're changing a lot of your kind of master of what should be the planning to that. And that is that switch you want to do is the major push for efficiency is to do that as few times as possible. And now we're doing them so many times. So this is really what it looks like, is that people are trying to solve this in a million different ways, and there's no clear answer right now because, for example, let's be cheeky, but even the Claude codebase was released and some of the agentic harness was shared. And I don't think even that was no one looked at that and said, oh, well, this is definitively the answer, I think in many ways, I think many people were oh, so they haven't figured it out. Do you know what I mean? After that happened. And that tells us that, whoa, this is a fun time, because it means that who cracks that balance and who can do that co-design well is really going to drive a lot of acceleration of how we all do it.
And I just want to say, I think it's so funny how all of these chaotic things and problems you describe as it's a fun time. You put a very nice spin on it.
Yeah, I mean, if you care about problems and you're curious, as long as you can see that they're within the realm of oh, if I can see how I can make progress on this, then typically it's more fun if they're bigger problems. Yeah, because it's oh, cool, the thing I care about, it's even, if I make progress on it, it's an even bigger impact.
Yeah.
Yeah, which maybe is a weird way of thinking about things, but.
No, I think it's great. It's great enthusiasm. We at Cerebras, we're building our own version of the AI processor, the Wafer-Scale Engine. It's largely intended to solve this memory bandwidth bottleneck that we see with GPUs. It is 7,000 times the memory movement than a GPU. What do you think suddenly becomes possible when we have newer architectures like this that are overcoming this memory wall?
I think what that is a bet on is the fact that so much is shifting towards inference, right? So inference, the memory challenges are twofold. One, typically people forget this, but we do way more. Most compute cost of a model is in inference. So we're just doing way more volume over time. And so how you handle that memory and how much you can extract in bulk and maintaining your throughput is really important. So having your chip also have your memory in place is the dream, because it means that you don't have as much movement. The second part is trickier, right? Because the sequential part of this, all these different you do something and then you want to do something else, how to handle that is going to be really interesting. And some of that is solved by this co-location of memory. Some of it's also solved by like, how do you do adaptive branching? And that's going to be the crux of it. And these two drivers are why we're seeing so much emphasis in memory in the space. But it is very true that if you can co-locate your memory, you are getting a lot more bang for your buck because you're avoiding this costly memory transfer. And inference has kind of been this perfect storm where even though training typically demands more memory because you're doing the backpropagation, the amount of inference we're doing and the fact that so much of our optimization is shifting to that means that inference really matters. And that's where I think chip design like that is really important. And again, we're lucky because we are deploying, research is product right now, which means in some ways, from one perspective, it means that we're very incentivized to innovate on hardware and algorithm co-design, which wasn't true for most of history. Typically, these disciplines never talked to each other, they had separate training, and it was only by accident if someone produced hardware that was useful for an algorithm. And now, in fact, it's like tightly bounded. So we're seeing way more chips that are very explicitly designed to maximize some of these algorithm problems in the deep learning space.
Are there any specific unlocks or things that you think will become possible in this new era where we have different architectures other than just the GPU?
I think about it as like, what are deep neural networks bad at? Because basically all our hardware is designed for that right now. So I think about it as like, okay, the main issue with deep neural networks is that it is extremely inefficient as a learning algorithm. And I think we forget that because it's just become the staple. But deep neural networks are essentially big frequency counters. They count how common something is and they learn that. And they're very hard to get to learn the long tail. That's because we use average error. So basically we try and minimize like the average error, which means that deep neural networks are good at what is common and high frequency, but it takes a lot of capacity, and often you have to 4x the size of your model, 10x the size of your model to get at those very rare artifacts. So what that means is the things that stray the most from our current hardware paradigm are also some of the most crucial for us to get right, because most of the real world is actually the long tail. And how do you learn the long tail as cheaply as possible is one of the most important questions right now.
Do you think what hardware is going to do is it's going to allow us to now explore different architectural directions altogether with models?
It's very tricky to get a hardware to serve differently overnight. In fact, part of the issue is that it requires so much capital and it has such a long timeline. People are very reluctant to innovate, especially if they know they can squeeze this one factor and get higher performance. So I think in the short term, what we'll see is main sources of innovation are going to come from two aspects. One is system, like how do you pair different types of hardware for these agentic, more sequential. The second is software's getting cheaper. So how do you switch between types of hardware much more swiftly? And like that is fun because traditionally you're very locked into your full stack. So I basically co-design with a single type. But if I can have an idea and it might not work that well on this type, but I can switch it within a day using software portability and better code generation to work on a different stack, that generally improves the speed of innovation because that teaches you, oh, this idea would work if it was only on this different hardware. So I think in the medium term, it's those. In the longer term, of course, the dream is a totally different type of hardware unlocks a new type of model. And we do have some new types of models. We have state space machines. We have some interesting things. We have capsule networks, which you might disagree or agree about whether they're groundbreaking, but they were doing something different, which is important. But I think that tends to be a longer term play.
Speaking of time horizons, in the original hardware lottery, you mentioned several ML techniques that were invented, but were not become popularized until decades later because they just weren't realistic or feasible. Are there any ML techniques that you see today that exist, but due to memory bandwidth limitations or things like that, were not possible?
A lot of memory bandwidth is gonna only be amplified by like some of the techniques that people are most excited about, like how do you do RL in the real world? How do you do sampling? There's still some techniques I mentioned in the hardware lottery that frankly I hoped we would see more progress on, but we haven't since I wrote the paper. I mean, unstructured sparsity is one of them. When I wrote the paper, there was people at Google working on what they believed would be hardware that could handle unstructured sparsity. And that would have been a huge unlock, because if you think about it, most of what our intelligence does is we don't take in all information. In fact, we discard most of it. We have log scale vision. We basically only notice important changes. We don't do a full forward backward pass, but that's because we're so good at handling unstructured data and unstructured matrices. We don't have to pack all our data. What's interesting is that I don't think that went anywhere. We had some hardware releases which were around very structured, predictable patterns, but that's not the same. So there's stuff like that that still exists, and probably a lot of it can be attributed to two things. It's been too lucrative to make deep neural networks better, so I think the hardware lottery got worse, frankly, for current hardware. The second is that it is just such a long timeline between each iteration. So like, I'm very optimistic about chip design and automated processes for that, to innovate more on how do we actually have a wider search space, because typically a faster search space or a larger search space spells innovation.
And so none of this is what resulted in the TPU?
No, I think the TPU was very much Google's bet on how do we maximize for this one attribute of performance. There are people who worked on it much more closely who can speak to it, but the TPU happened with the catalyst was after deep neural networks really became popular. And so the TPU was very much a response to that, like saying, we're going to optimize for this one workload. And in fact, the positioning was, we're moving away from general purpose computing. So we're not going to allow for every idea to succeed. We're going to acknowledge that TPU may kill a lot of ideas. And so anyone who's worked on a TPU knows this. It is very much specialized for a few set of workloads and making those go very fast. But if your workload is one of those, you love it, because it extracts every ounce of performance. But no, TPU was really meant for doubling down on the success of deep neural networks. And arguably that, in some ways, just reinforces the lottery, but it doesn't create new winners. It's almost like the jackpot just gets bigger, but there's only going to be a single winner.
So if you had to design a chip specifically for adaptation, how would you think about it?
We talked about some of the problems with current architecture, like how you handle memory is going to be really important. But to be honest, like adaptation isn't in the chip business. In fact, to be in the chip business, typically you're in a very tricky position where you can't innovate as much, because you have to kind of calculate just the right amount of resources to pour in to maximize the fact that it will still be compatible with the current ideas in 2 or 3 years. There are people who take those bets. For me, it's always been more interesting to hopefully like craft the next set of ideas that motivates the next generation of hardware. And it's that catch up and interplay cycle that's really interesting. That being said, really crucial for us is we really care about co-design with serving and with our current set of hardware, because we think that's crucial to just squeeze out at maximum performance.
I know that, conferences like NeurIPS are still 6 months away, but do you have a prediction for what you think like the big theme of 2026 or the hottest topics might be?
Oof, I think it's gonna be, I feel like there's already been so much that's happened in 2026. Like if you think about it, we've had someone propose data centers in space, not to be named. We've had like,
well, the GPU is already in space.
Yeah, yeah. But even that's wild, right? Like, how are the cost economics of that make sense? It's just crazy. Then we've had multiple frontier labs just have wildly different predictions about where they want to go. Like, we've had code reds at some frontier labs saying it's all about code. One of the reasons you have bets like adaptation is that you can no longer get away with just scaling your model size. And so I actually think NeurIPS, it's going to be way more about the recipe. And unfortunately, I don't think anyone's going to talk about the recipe. I don't think that will change, but it's going to be way more about that. Like, how are you leveraging all this post-training compute, and how are you thinking about like this interaction component? Instead, for the last few years, it's been all about guessing the parameter sizes of models. And that was such a boring trend. Like if you think about it, like how boring could we be that we were all like, oh, and what do you think their model size is? So in some ways, I feel like it's a refreshing break, but there'll still be a healthy dose of like the pace and honestly the calculation of what's going to lead to the next breakthrough. is probably not going to come at Europe. It's going to come throughout the year, and then we'll just digest it in Europe and be like, whoa, what a year. Which is what has also happened for the last few years. The research that is presented there matters less because so much has happened throughout the year.
Do you think that the reason that people started pivoting away from just caring about model size is because we had so many open source models that you know the exact parameter size? It took away a lot of the guessing.
Yeah, I also think it's because there's been a converging in performance between open and closed. And it's also because no closed model, there's been experiments in expanding the size within closed settings, and it hasn't given the returns that people expected. So I think just model size as a variable for innovation has just started to matter less. I think what you do with a model and how expressive your output space means that you can invent a lot more things in the output space. You can have these recursive self-improvement loops. That started to matter more. And that is less about the size of the model. It's more about how you leverage the system. So the focus is just moving towards the system.
Well, Sarah, thank you so much for joining us today.
Oh, it's lovely. Really nice chat. Great to be here.